So domain and range. The domain of a function, these are properties of functions. The domain of a function is the set of all inputs. And the range of the function is the set of all outputs. So every input the function can take, every output the function can give. That's the domain and range. For example, if I said, let f be a function where f of 1 equals 4, f of 2 equals 5, and f of 3 equals 6 only. And there are no other points that I can plug in. That is it. That is all this function does. I'm allowed to do that. I'm allowed to say you can't plug in any other points. I can define the function however I want. This is a valid function. Then I could write that the domain of f is the set of numbers 1, 2, and 3. And the range of f is the numbers 4, 5, and 6. Okay? So the domain is all the inputs we can have. The range is all the outputs we can have. Sometimes I'll draw these in a little diagram like this. Here's the domain, here's the range. So we think of the function as being a mapping where it takes points in the domain and moves them over to the range. So the domain has points 1, 2, and 3. The range has points 4, 5, and 6. And the function maps 1 to 4, 2 to 5, and 3 to 6. And that's how I would draw that. So these diagrams can sometimes be useful when trying to understand how functions behave. So I'll be drawing a few more of these, especially in the inverse function section, since that's a pretty technical subject. I mean, it's not too bad. It's inverse function just means doing the function backwards. So there are some quirks that we'll have to pick out with diagrams like these, but nothing too awful. Don't worry. So let's talk about the domain and range of, let me draw some example graphs, and then we'll talk about our toolkit functions, and then we'll talk about some other functions. So let's say I have a function whose graph looks like this. Let's say this is the point 4, 5, and this is the point -3, -2. So here's our x values, and here's our y values. The domain is the set of every x value that appears on the graph. So we always go from left to right, so from smallest to biggest x value. So the smallest x value that can appear on, the x values that can appear on the graph, I can't say the smallest because this is an open circle. I know that's a very nitpicky detail, but what I should say is any x value that's bigger than 3, bigger than -3, and smaller than 4, smaller than or equal to 4, any of those x values can fit on the graph. If it helps, think of a light that casts a shadow down onto the x-axis. Actually, the technical term is projection. So think of like a overhead projector. And that shadow is the domain. So it's casting that shadow straight up and down. Those are all of the x values that can show up on the graph. It's any x value starting at -3 and going up to 4. So I would say that for this graph, the domain is, it starts at -3 but doesn't include it, and it goes up to a 4 and does include that. So this is how the domain looks as an interval. It's every number between -3 and 4, including 4, but not including -3. The range is actually pretty much the same idea, but with y values. So for y values, we're always going to go from bottom to top, since we still want to go from smallest to biggest. So imagine that projection onto the y-axis. You can say projection or shadow. They mean the same thing, but I'm just telling you that in a lot of textbooks I've seen, the word projection is the one they use, just in case you're reading one of those later. So these are all the y values that are represented on the graph. Do you see? Because this y value is here, this y value is here, this y value is here, this y value is here. So those are all the y values on the graph. They start at -2, but don't include it. They go all the way up to 5, and they do include that one. So we're looking at y values now. The lowest y value is this -2. The highest y value is this 5. So the range is from -2 to 5. 5 gets a bracket because it's included. -2 gets a parenthesis because it's not included. And that's just because of the open circle there. So that's how you'd find domain and range from a graph. Let's do one that's just slightly trickier, just because there's one like this in the homework, and I know it traditionally gives people a lot of trouble. Let's say I have part of a kind of parabola-shaped curve, and let's say it looks like, no, hold on. I like it better if it looks like this. So this bottom out point here, let's say that that's 0, -3. Let's say that this point is 3, 1, and let's say that this point is -2, 8. The domain is pretty straightforward. We can just look at the x values from left to right and go from the smallest one to the biggest one. So following the curve of the graph, the smallest one is -2 and the biggest one is 3. So the domain should be from -2 to 3. You see I do a bracket for the point that's included, a parenthesis for the point that isn't, but the main point of this exercise is that the domain is all of the x values we can see. If you want, you can draw that like a shadow. Project it down, project it up, project it down again. So there's an open circle here, a closed circle here, and it's all of these values. Now I have a lot of people get confused on trying to find the range on this one. So take a moment and see what you think it might be. It's all the y values that show up on the graph from lowest to biggest, and where a lot of the confusion arises is our natural instinct is to want to follow the curve. But that's not where the y values start and stop. The lowest y value is right here. That's the bottom point of the graph. That's the minimum, is what we'll say. And the highest y value is all the way up here. And all the y values in between are represented. So it turns out that this point out on the right doesn't really matter to the range. These points, these y values were already covered on this side. So these y values are covered twice, in fact. But the range is from the lowest y value up to the highest. And so the range of this function is from -3 to +8. And both of those are included because those are both points that are actually on the graph. So that's the range of this function. Hopefully that makes more sense now that you've seen it. So the next thing I want to do is look at the toolkit functions and decide on the domain and range for each of these. Let's start with function. We're going to go a little bit out of order. If there is no restriction, I can plug any number into this. It just says you get out whatever you put in. So no matter what number I pick, that's fine as an input. I can pick 1,000,000 or -6, and I'll get that number back as an output. So there isn't any number I can't put in, and there isn't any number I can't get out. So I'll write the domain and the range are both all real numbers. And I can either write that with the fancy R or with this interval, all the numbers between -infinity and +infinity. For the absolute value function, I'm going to do this one next. The domain is still all real numbers. So there's no number I can't plug in. But now the range is limited. There's no way to get a negative number out of the absolute value function. The smallest number I can get is 0. I can get a 0, and I can get any positive number. So the range starts at 0, and 0 is included. So that's a dicey part. You have to make the choice of whether the endpoint is included, and it's based on the specifics of the problem. Here, the bottom is included because 0, 0 is a real point on the graph. And then that can go up as high as you want. So the range is 0 to infinity. All right, with that under our belts, let's tackle the constant function. This one's really goofy. The domain is still all real numbers. There's no limit on what we can plug in. But the range, this one's pretty goofy. What numbers can I get as my output? Just C. C is the only output we can get. So the range is just C. I'm going to write it with curly braces. So I'm going to say the range is a set of outputs, and it's the set with only one element, and that element is C. There isn't really a good way to write a singleton set with interval notation. I guess you could do square braces C comma C, but that feels wrong to me somehow. I've never seen that in a textbook. I don't think it's conventional. This is the normal way to write it. X squared. It's curvy instead of pointy, but in terms of domain and range, it's the same as the absolute value. You can put any number in, but you can only get 0 or positive numbers out. So you can put any number in, negative infinity to infinity, but the only numbers you can get out are, you can get 0. 0 squared is 0, so 0 works, so I'll put that with a bracket. And any positive number works, so I'll go up to infinity with a parenthesis. The cubic function, I can put anything in, and I can get anything out. The rule with domains and ranges is if there isn't some restriction on them, it's just going to be all real numbers. 1 over x is a tough case. For 1 over x, I can put almost any number in. The only restriction is right here. You cannot divide by 0. So the domain is any number except for 0. So any negative number works, or any positive number works. So I've wrote all the negatives and all the positives. The range is actually the same way. Notice there's no way to get a 0 as the output of this function. You can get any other number, just not 0. So the range is the same. The reciprocal squared here, this is not like any of the ones we've seen before. The domain is the same as the reciprocal. I can put in any number as long as it's not 0. So all the negatives, union, all the positives. If I put in a 0, I'd be dividing by 0 squared, which is still 0. As for the range, I can't get 0, but now I can't get any negative numbers either, because squares are always positive. So the range is 0 to infinity, but the 0 has a parenthesis this time. For the square root function, I can't put a negative number in, and I can't get a negative number out. If I put a negative number in, I'd get a complex number, and we're not doing that with functions. We're just doing real valued functions in this class. So I say that the domain is positive numbers and 0. The square root of 0 is 0, so that's just fine. And the range is 0 and positive numbers. The square root of 0 is 0, so that's the first number. And then it goes all the way up to infinity. Remember, you can think of it as a projection. The domain is every number on the x-axis here, 0 and above. The range is every number on the shadow on the y-axis here, 0 and above. And I know the graph looks like it stops at 3 or 4, but that's only because I didn't draw it all the way out to the edge of the screen. It keeps going up forever. It never levels off completely. Same with the cubed root. It never levels off completely. It's going to keep going up forever. If I want a y value of 1,000,000, I have to go really far out to get it. I have to go out to 1,000,000,000 billion, but I can do it. So the domain is, of course, all real numbers. There's nothing I can't take the cubed root of. And the range is also all real numbers. In my open math, the way you write an infinity, by the way, is you put the letter O twice. It might be useful to you as you're doing domains and ranges. Then again, you probably saw those when we did inequalities before, so that's probably still news at this point. All right, so that's the domains and ranges of the toolkit functions. I'll come back to those one more time in this lecture as we talk about, hey, where are my 3.3 notes? Oh, these are my 3.3, okay. I'm sorry, I confused myself again. You know how it is. Maybe you don't. I just remembered that my notes for this section cover both 3.2 and 3.3. So I'll have to make a note that this series of videos is probably going to be 4 parts, and it's going to cover all of those. So let's finish up domain and range a bit. In general, range is harder to find than domain is, actually. That's the general truth of it. So for some of these, I'm just going to ask for the domain and not the range. But not this first one. Let's say we let f of x, and I have a bad habit of just using f over and over, so you'll have to understand from now on it's going to be a new function every example. I'll draw horizontal lines between examples. It's just going to be a new function even if I keep calling it by the same name. F for function. It's the standard choice. It's the standard choice. So let's say f of x is x squared minus 1. Oh, I should probably say this colon equals thing, that's, I took that from computer programming. Your textbook doesn't do that, so don't get weirded out when it's missing from your textbook or Khan Academy or whatever. I don't think most mathematicians do that, but it helps me keep things straight when I'm writing, so I like to use it. So let's say let f of x equal x squared minus 1. A problem could be something like find the domain and range of f. Now the rule for domain is unless there's some reason you couldn't plug things in, you're allowed to plug them in. So we're going to say that the domain is all real numbers. I'm going to stop writing the interval negative infinity to infinity here. I'm just going to write all real numbers. There's no number I can't plug into f. So let me make a note here. R is the shorthand for the set of all real numbers. So it's that interval. So now I'm just going to write R. As for the range, ranges are usually pretty tricky to find, so I won't ask you about them very often. In this case, we have to look at the graph of x squared plus 1, or x squared minus 1, and see if we could come up with anything special about it. So if I plug in 0, I just get 0 squared minus 1, that's negative 1. If I plug in 1, I get 1 squared minus 1, that's 0. If I plug in negative 1, I get the same thing. If I plug in 2, I get 4 minus 1, which is 3. And 3 gets me 9 minus 1, which is 8. Same on the other side. In fact, this shape is a parabola again. If you compare it to the parabola for x squared, you might notice it's that whole thing, but it's moved down by 1 unit. So I took the output from x squared, and then I subtracted 1 unit from all of my outputs. So it looks like the regular parabola from the toolkit function, but just moved down by 1. We'll explore the consequences of that in section 3.4. So that's the first section of unit 3. We'll explore how we can use modifications like this. So this modification of a -1 moved the whole graph down by 1 unit. We'll explore moving graphs up, down, left, and right, stretching and shrinking them, flipping them, rotating them. It'll be a grand old time. Right now, though, the implications are that the range Well, the range starts here at -1, and then that shadow goes all the way up to infinity. So that's our range, -1 up to infinity. And -1 gets a bracket because 0, -1 is a point on the graph. So that point is represented, so it's included in the interval. So that's the domain and range of f. I could do something like this. What is the domain of, here, let's make this a two-parter. Let's say g of x equals 1 over x minus 1. And let's say h of x equals root 4 minus x. This is going to highlight the restrictions we have on domain so far, in fact. So remember, these are modified versions of Toolkit functions. Let's take a look at those real quick. There's the reciprocal function, where I can't divide by 0. And there's the square root function, where I can't take the square root of a negative number. So back down here, I'm going to write those down. Can't divide by 0, can't square root a negative. I'm just going to use shorthand there. You know what that means. Can't divide by 0, can't take the square root of a negative. In fact, these two bullet points here in red are the only restrictions we have on domain so far. In Unit 4, we'll get one more restriction, but for now it's just these two. If the function doesn't involve division and it doesn't involve any square roots, then the domain is always going to be all real numbers, every time, until we get to Unit 4, but I'll let you know when that happens. So until then, we can assume that. So what are the domains of these functions? If I can't divide by 0, then I can't have x minus 1 equals 0. So that has to be not equal to 0. I'll add 1 to each side. X can be equal to 1. So that's the domain. Every number except for 1. Now on a number line, that would look like here's 0, here's 1. There's a big circle at 1. Any number that's bigger even slightly works. Any number that's even slightly smaller also works. I'm not asking about the range of g because that gets tricky, but for the domain of, it should be -infinity up to 1, not including 1, and then 1 up to infinity, again, not including 1. So this is every real number except for 1. Part B. H of x is the square root of 4 minus x. We cannot square root it. So what I know is 4 minus x is not negative. You know how I write the numbers that aren't negative? We learned about this in section 2.7. The way I write those is I say 4 minus x has to be 0 or bigger. If it's not negative, then it has to be 0 or bigger than 0. So I write 4 minus x is greater than or equal to 0. That assures that it's not negative. That's exactly this statement. This is the English statement. This is the mathematical statement. I've just translated from one language to the other here. So 4 minus x has to be greater than or equal to 0. I'll add x to each side. 4 has to be greater than or equal to x. So my solutions are x can be, here's 4. 4 works. Any number x is less than or equal to 4. So any number less than or equal to 4 also works, because 4 is greater than or equal to x. So my solution set says the domain of H is any number bigger than -infinity and no bigger than 4. So 4 gets a bracket. Let me on part C. Jeez. Let's call this f of x, because I've run out of names again, so I'm recycling. Let's call this f of x is, and this is going to be a crazy one, root x plus 3 divided by x plus 2. Now both rules are in play. Can't divide by 0, so x plus 2 cannot be 0. That means x cannot be negative 2. So if x is negative 2, we're dividing by 0, and that's no good. But how about the numerator? I can't take the square root of a negative either. So that means that x plus 3 cannot be any smaller than 0. X plus 3 cannot be any smaller than 0. Subtract 3 from each side. X can't be any smaller than negative 3. So here's my solution set. Here's 0. I'd better draw negative 2 and negative 3. It can't be any smaller than negative 3, so negative 3 is the minimum. If I plug in negative 3, everything works. It's the square root of 0 divided by negative 1. That's 0, so that's fine. Anything even a tiny bit smaller, and we're into complex territory, and that doesn't fit with functions. But now, it should be any number bigger than negative 3, but there's one exception. If I plug in a negative 2, I'm going to be dividing by 0. So I have to cut that one out, put a circle there, like so. Then any other number than that one that's bigger than negative 3 is just fine. So I'll shade in all the numbers to infinity. Now let's write this. This is two different intervals. There's a tiny one here and a giant one here. So I'm going to say the domain of f is, first interval, we'll go from left to right always, from negative 3 up to negative 2. And then the other interval, so I'll use a union symbol, is from negative 2 up to infinity. And that is the domain of that function. All right. So that's domains. In the next part of the video, let's talk briefly, so the next one will be short. Next, I want to talk about something called a piecewise defined function. So join me after the jump.